Hello, my name is Oleg Demin Jr. and I am a scientific and marketing director in Insys Bio. And today I will talk about the implementation of variability or uncertainty in parameter values to validate mechanistic models. Validation is an important step to test the reliability of the mechanistic models. Usually to validate the models we use the clinical endpoints measured for the population of patients. This can be percent of responders or mean and standard deviation or standard error of the particular biomarker. Thus, variability should be implemented to describe clinical data. Let's do one step aside to briefly talk about the validation. So model validation is a process by which model outputs are compared to independent observations, which was not used for fitting or calibration, to judge the quantitative and qualitative correspondence with the reality. So validation is a context dependent. Unfortunately, there are no absolute criteria to assess the quality of validation. Moreover, validation of one model can be quite different from the validation of another model. For example, validation can be done in the following manner. So if you have clinical data on the particular drug, you can divide this data into the two parts and use first part for the model fitting and the second for the validation. Another case is when you have clinical data for the two drugs and you use the clinical data on the first drug for the model fitting and data on the second drug for the model validation. So, in general, validation is another very complex and interesting question in the QSP modeling, um, and should be discussed, of course, separately. I just would like to mention only the open webinar that was held a few months ago regarding the validation of systems morphology models. So, there are two ways of variability implementation in the parameters. First is the uncertainty of fitted parameters. So, for the fitted parameters, we can calculate 95 confidence intervals. And these intervals include some information about interpatient variability, especially when it is based on the experimental data from different sources, so different patient groups. The second general approach is the direct generation of the virtual patient population. There are various approaches to generate virtual patients. First of all, I would like to illustrate the variability taken from the uncertainty of the fitted parameters. And here is the first example. It is the semi-mechanistic model of SGLT2 inhibitors. In framework of this model, we used part of the PK clinical data to feed the model parameters. And then we were able to identify 95 confidence intervals for these fitted parameters using profile likelihood methods. The second part of the clinical PK data was used to validate the models. So on the basis of the 95 confidence intervals, we simulate the 95 confidence bands for the model predictions and then compare it with clinical data. You can see example of the validation in the right side of the slide. Another example is the QSP model of asthma treatment with anti-cytokine therapies, which was published by my colleague from Institute by Tatiana Karelin and co-authors. This model was fitted against the data on the baseline levels of cells and cytokines in blood and airways. Then Hessian matrix was obtained for the fitted parameters, and then 95 confidence bands were simulated for the model predictions on the basis of this Hessian matrix. In case of this model, all clinical data on patient treatment was used only for validation. And you can see the examples of validation and predictions on the right side of the slide. Second general approach is the generation of virtual patient population. There are at least several published manuscripts describing different methods and approaches to generate virtual patient populations. I decided to use to show you this manuscript and this approach, which was published by Allen and co-authors in 2016. So the general idea of the approach is the following. So first of all, you put a wide ranges for the parameters, for example, physiological ranges. Then you generate large number of virtual patient population, and this large cohort is called plausible population. Uh, in case presented in this article, 300,000 patients were simulated for the plausible population. Then the authors selected virtual patients to match the clinical data using proposed methods. Um, you can see the illustration of this approach on the right side of the slide. Upper figures represents how the uh, large cohort of patients, plausible, called plausible population, describes the data, where the black curve is the data, and the red curve represents the model predictions. And then when some small population of patients is selected, the data can be described quite well. Another approach that I would like to mention is the poster of my colleague Galina Kolesova. She's considering four approaches to generate virtual patient populations, and I will briefly talk about two of them. Approach number two is the fitting to Monte Carlo sample, and the idea of this approach is when you have individual data, or you can generate individual data on the basis of the mean and standard deviation. You can feed each individual patient separately and feed the parameters for each patient, and then you can analyze these parameters and identify the distribution for these fitted parameters. And on the basis of this identified distribution, you can generate the virtual patient population. This approach is quite straightforward. Approach number four is stochastically bound selection. So it is in general quite similar to the published approaches, including approach presented on the previous slide. So the idea of this approach is to put some wide ranges for the parameters, like some physiological ranges, then to generate large cohort of virtual patient population, and then select n virtual patients from this generated large cohort to match clinical data using proposed methods, where n is the number of patients in clinical trial. If you would like to learn more, please look at the poster of my colleague, which is available on our website. The third approach that I would like to discuss is the approach that I use in my practice. The idea of this approach is to choose the distributions and parameters of the distributions for the variable parameters and the baselines on the basis of the available data in vitro, ex vivo, in vivo, and so on, and then predict the clinical data. So there are following steps. So we identify and implement variability in the parameters and the baselines. Then we generate the virtual patient population with required number of virtual patients on the basis of these identified distributions, and compare model simulations with clinical data. And if everything is okay, then we can apply the model. If the model cannot describe data accurately, we have to recalibrate the variability of one or two key parameters, standard deviation or type of the distribution. Uh, Usually, if the model parameters are well defined on the basis of the available data in vitro, ex vivo, and so on, it is likely that the model will successfully describe variability and mean median of the clinical data. But if the key parameters cannot be defined accurately, usually calibration of variability is required. And this approach we applied in multiple oncology and immuno-oncology QSP models, as well as PPK-RAW models of small molecules and therapeutic antibodies. In framework of this approach, we implement variability in the following parameters and species. First of all, this is the baseline levels of the cells and cytokines, including tumor cells in different compartments. Also, it is expression, concentration, number of target molecules or receptors. Of course, we implement variability in the key parameters of the described therapies. Another one is the effect of the therapy if it is described in same mechanistic way, like parameters like Imax, IC50, Emax, EC50. So if you have more mechanistic description, like you have the antibody which binds to the target, you can vary the expression of the target receptor as well as the parameters of the signaling caused by ligation of this target receptor and its effect on the processes described in the model. Of course, variability should be implemented in the tumor growth rate as well as in the effects of the regulatory molecules. And finally, variability is also implemented in the cell functioning processes like apoptosis, activation, migration. It can be implemented in the rate constants, if it is described in empirical manner, or if it is described in more mechanistic way, we can also implement the variability in the levels of the concentrations of the regulators of these processes as well as in the parameters of the regulation. And of course, there are some parameters where variability is usually not required. These can be the affinity parameters like dissociation constant and KF value. Also, it can be some processes or species where we do not have enough data and which are not so important for the model prediction. But in general, my own point of view is that we need to introduce the variability and identify as much parameters as we can because the more parameters you identify, the better predictive power of the model you will have. Of course, it depends on the size of the model and its feature. For example, if you have model with thousands of equations, I'm not quite sure that it is possible to identify and implement variability in all necessary parameters due to the deadlines in the project. Uh, but anyway, we can try at least to implement only in the variability in the key parameters of the model. To illustrate this approach, the third approach, I would like to show you first of all the Vitoro model of BTK inhibitors. This model was used to predict the data of the BTK occupancy in different compartments such as blood, lymph nodes, and bone marrow. And here we use all clinical data on the BTK occupancy only for validation. So the model, the variability was introduced on the basis of in the key model parameters on the basis of the other available data, such as clinical PK data, in vitro and ex vivo data. So you can see the example of the model validation on the right side of the slide. Another example illustrating this approach is PPKRO model of anti-PD-1 antibodies. The idea of this model was to predict pharmacokinetics of the antibodies without any fitting or calibration against the clinical PK data. So again, here the variability was introduced in the key model parameters such as physiological parameters, number of endothelial cells, T cells which express PD-1, of course the expression of the receptors. And then we just simulate pharmacokinetics and compare it with the clinical data. You can see the examples of the validation on the right side of the slide. To summarize, in general, there are two strategies of the generation of virtual patient populations. First is when you generate a large number of virtual patients on the basis of the wide ranges for the parameters, for example, physiological ranges, and then you select the virtual patients from this large cohort to match particular clinical data using one of the proposed or published methods. One of the important thing here is that this selection is something like fitting. So I think here it is important to have another data set which can be used for the validation of the selected virtual patient population. And the second approach is when you identify the distributions and ranges for the parameters on the basis of the various types of the data in vitro ex vivo and so on, and you assume that these is ranges and distributions are true, and then you generate virtual patients population without any selection of particular virtual patients, and just compare the predictions with clinical data. Of course, using the in case of this approach, some recalibration may be required. Um, and finally, conclusions. So I think the generation of virtual patient population is a very important topic in the QSP field, and we need to further work on the methods to generate virtual patients populations to validate the models. So in general, at the high level, there are two strategies to generate virtual patient populations. Both strategies have advantages and disadvantages. I will not I didn't talk about them, but I would like to mention one key issue. This issue is the required computing time. The multiple simulations usually require a lot of time, and not all modelers have the access or infrastructure to use the clusters or supercomputers to increase the speed of the simulations. So the QSP community need to further improve the approaches of generation of virtual patient populations. I don't know whether it is possible to develop some universal approach for different types of models or not. Maybe some combination of developed approaches might be a solution. Or, for example, we can develop a list of approaches, and the user will be able to choose among these approaches and choose any of these approaches based on the features of his or her model. Um, so I would like to thank you for attention, and also I would like to thank my colleague Galina Kolesova. She helps me to prepare the slides and other posters and talks from Insis Bio at SMB 2021. You can find at our website as well as other our posters and publication. Thank you.